So let's next, consider the graphs of these hyperbolic functions. Now remember, this is defined as e to the x plus e to the negative x all over 2. So to sketch this graph, I'm merely going to use graphical addition. Let's first consider the graph of this equation. In red, and the graph of this equation in blue. They both have a y-intercept at 0, 1/2. So on the graph of this black equation, I'll add those two y values of 1/2 and 1/2, and I get a y-intercept for the graph of the hyperbolic cosine function at 0, 1. Now, as x increases with that bound, the corresponding y values in blue are going to 0. So the further and further I am to the right on the graph of this equation, I'm adding to these red y values numbers that are getting closer and closer to 0. So I think that red curve is going to behave asymptotically with the graph of this equation in the right-hand plane. And for the same reason, I will have this blue curve acting asymptotically with the graph of the equation I'm trying to construct. Now over here, if I use graphical addition with the graph of this equation, and the graph of this equation, here's what I get in black. And that will represent the graph of my hyperbolic sine function because the output of this function we already defined as a sum of these two outputs. Now, if you take a peek at the graph of this equation, if you take all the y values on this black curve, divide by all the y values on that black curve, then as x increases that bound, that ratio is getting closer and closer to 1. At x equals 0, the ratio of the y values here to here are 0 to 1, which is just 0. So clearly, I must behave as such in the right-hand plane. In the left-hand plane, I have the same darn ratio of y values, but with a sign change. Now, to sketch the graph of these three equations here, here, and here is just so easy, graphically speaking, because I've already defined the output of this function to be the reciprocal of the outputs of this function. So when x is equal to 0, the y value on that curve is positive 1. Its reciprocal is still positive 1. Now, as x increases that bound, the y values increase that bound, so the reciprocals are getting closer and closer to 0. Same thing in the left-hand plane. Can you appreciate how here the domain is 0 to 1, not included in the left endpoint, but included in the right endpoint? Now here, reciprocating all the y values you see in black, well, notice when x is equal to 0, its reciprocal is undefined. But same behavior in the right-hand plane is over here, in the sense that my y values are going to increase that bound, and so they're getting closer and closer to 0. But immediately to the right of the y-axis, since these y values are so small, their reciprocals are very large. And so I think, globally speaking, here's what the graph of this function should look like in the right-hand plane. Same in the left-hand plane, merely with a sign change. And lastly, reciprocating all the y values in this curve, wouldn't you appreciate I just get this curve? There's a graph of my hyperbolic cotangent of x. So I need you to be familiar with those graphs, but I haven't discussed any calculus with my hyperbolic functions. Let's dive in. I'm too tired, I'm too lazy to go back to my man-made definition of the derivative function, so I will cheat. The 1/2 gets pulled out. Differentiating the first term and differentiating the second term with the chain rule. But in the end, isn't that just this? using exactly the same process. Down here, I should get this. Notice, unlike with my circular functions, I don't get a sign change here. Now, next on my list, would you not agree? Now using the quotient rule. And then running out of room. There's my downstairs, times the dirt of the upstairs, minus the upstairs, times the dirt of the downstairs, but I'm running out of room, so can I cheat? All over my denominator, squared. Now, with a corresponding Pythagorean identity for my hyperbolic functions, that numerator is just 1. There is nothing wrong with what I'm writing. But because back in both trigonometry and this semester with calculus, we've seen so many intimate relationships between the tangent function and the secant function, I'd like to see a corresponding intimate relationship between the inverse, excuse me, misspoke. I'd like to see an intimate relationship between the hyperbolic tangent function and the hyperbolic secant function, and I can. Because I think without squaring, that's merely the reciprocal of the hyperbolic cosine of x, which I defined as this new function. It's just being squared. I think you know what's next. Using the quotient rule. The first term drops out. Or how about saying more conveniently? And how about if I leave these last two for you? Better. Notice how all three of these have a -1 factor.